We've introduced ordinary least squares, the regression. We've also looked at some examples and we've calculated the regression line by hand. Now let's talk about the assumptions required to estimate a plausible regression line. Our goal here is we want to find out how x affects y, all else equal, or everything else held constant. As an example, we might want to know how much do wages increase with an additional year of schooling for men ages 40 to 50. In this example, we're implicitly holding sex and age fixed. How do we do that with a regression line? That's where we're going in this class. We're not getting there yet, but that's the idea. To get at this, we need some restrictions on how the error term u is related to the independent variable x. Suppose we have this regression model, yi equals beta 0 plus beta 1 xi plus ui. Note that these are just the variables in our data set, and they're all indexed by the rows in our data. One thing I haven't mentioned yet is that the beta 0 and beta 1 are constants, at least in the population regression. But for the sample regression, even if we put hats on these are the same. We're implicitly assuming that these are the same for every person or every observation in our data set, right? So these are not, betas are not indexed by I. There's no I there. So what we're getting is the average relationship between y and x. Assumption number 1, the expected value of u, the error term, is equal to 0, or the average of the value of the population error is 0. This assumption is fairly benign in that all we need to do is rescale the error term such that the average value is 0. And we do that by adjusting the intercept. In other words, we're shifting the line up and down. This assumption says nothing about the relationship between u and x, but it is used to define beta hat 1. This one is not too difficult. Assumption number 2, the expected value of u conditional on x, remember this line here means conditional on x, is equal to the expected value of u, which is equal to 0. So this is using the first assumption, and this is called mean independence. The average value of u does not depend on x, and this is a formal mathematical statement about other factors contained in u, perhaps the most important assumption when we run a regression. It implies that u and x are uncorrelated. Given any x value, the mean of the distribution of u is 0. So let's look at this in a graph. What we're talking about here is this distribution is the same regardless of what x value we're talking about. The distribution of u does not depend on x. A benchmark for thinking about this assumption is to consider an idealized randomized controlled experiment. If x is some sort of treatment and it's randomly assigned to people, maybe we have students randomly assigned to different class sizes and the treatment is the class size, or patients randomly assigned to medical treatments. Oftentimes patients receive either the actual vaccine or a placebo. Because x is randomly assigned, all other individual characteristics such as ability, income, or underlying health conditions are independent of x. Right? So we don't want people that are more healthy or less healthy on average receiving the vaccine. We want a person's health to be independent of whether or not they receive a vaccine versus a placebo. What this means is that the u, the error term, things contained in the error term like health conditions, the distribution of the health conditions are independent of getting the treatment. That's what this statement formally means. In actual experiments or with observational data, most often in econometrics we're using observational data, we have to think hard about whether or not this is true. Example 1, take the wage and education example. So we have our regression line. Is this population or sample? It's population because there's no hats on these betas. Suppose the UI is equal to ability, and ability is unobserved. Assumption 2 says that the average level of ability is independent of the level of education a person obtains. Is this plausible? What this means is assumption 2 says that expected value of ability conditional on education equals 8 years is the same as the expected value of ability conditional on education equals 14 years. So people with 14 years of education have the same ability levels of people, on average, as the people with 8 years of education. Is this plausible? Not necessarily. It could be that the average ability increases with years of education, or those people that are naturally better at college tend to go further in school. Another example of when assumption 2 fails. Student math performance in school lunch programs. Let math denote the percentage of 10th graders passing a standardized math exam, and let lunch program, this thing here, denote the percentage of students enrolled in a free lunch program. The regression equation is this. We're relating lunch programs to passing the percentage of 10th graders passing in the standardized exam, and U is going to contain school and student characteristics that affect overall school and student performance. So if we had data and we estimated this naive regression line, we might get the following sample regression equation. So this is a sample, right, because we have a hat there. This regression says that if the number of students in lunch programs goes up by 10%, then the percentage of students passing the exam goes down by 3.2%. That there. What we're really doing, if you're curious, is this is measured. A 1 unit change would be 0.319, but we're taking a 10% change, and so we're moving that decimal over by 1, so we get 3.2%. Do we believe this? Can enrollment in a lunch program cause math scores to go down? Maybe, but really, the fact that you're getting free lunch shouldn't affect your test score. A better explanation is that U contains factors that are correlated with lunch program. In other words, assumption 2 is failing. Expected value of the error term conditional on X does not equal 0. What could be contained in U? Poverty rates affect student performance and also enrollment in a free lunch program. So if poverty rates are affecting poverty rates are probably affecting the percentage of students enrolled in a free lunch program, right? As the poverty rates go up, more students are going to be enrolled in a free lunch. But also, as the poverty rates go up, the parents of the children in those districts or in those classes are going to have less time to spend with their kids helping them with their homework, because those parents are probably working 2 jobs to make ends meet. Also, parents in poverty might have less education themselves, and so they don't really necessarily understand the value of education or understand the material themselves. And so the students are more or less left to their own devices to pass the classes. And so students that are in higher areas with poverty spend less time with their parents helping them with their homework, and so therefore they get lower scores on the math tests. And so it's not really the fact that the students are enrolled in the free lunch program that's causing them to get lower test scores. It's the fact that the students enrolled in the free lunch program are also in higher poverty areas where the parents have less time to spend with them. Also, school quality and resources could be contained in the error term, which could affect both those variables. Assumption number 3. The X and the Y are IID, independently and identically distributed. This is true if X and Y are collected via random sampling. This provides the sampling distribution of beta hat 0 and beta hat 1 by what? The central limit theorem. Arises automatically if the data is sampled via random sampling. That's great. Assumption number 4, large outliers of X and Y are rare. What do we mean by outliers? Well, outliers is sort of fuzzy. What the problem with an outlier, so suppose that we didn't have this data point here, the one that I just circled. Alright, a regression line, OLS would estimate the regression line here, which is basically flat. In other words, the beta hat 1 would equal 0. But if we have an outlier, that single point could pull the regression line upwards. I should write it like that. That single point could pull the regression line upwards, causing beta 1 to be greater than 0, but it's really only driven by this one observation, which might be mismeasured. And so there might not actually be a relationship between x and y. Instead, it's that this data point is spuriously pulling that line upwards. So that finishes up the assumptions for ordinary least squares. Number 2, we'll talk about in a lot of detail going forward when things contained in the error term are correlated with the x value.